Okay, in this tutorial we're looking at 6.7, which is all about rates of change. Okay, so just remember a couple of things with our average rate of change is it's f of x2 minus f of x1 over x2 take x1, or as we know it a bit more as our rise over run formula of y2 minus y1 over x2 minus x1. Okay. To solve rate of change problems, we want to draw a diagram, identify the rate of change required, and define the variables. Express the quantity that is changing as a function of one variable, the variable the rate is measured with respect to. Find the derivative that measures the rate of change, substitute the given value into the derivative expression, and remember that a negative rate of change means the quantity is decreasing. Okay, so we'll have a look at one of these type of problems. Okay, so this is going to be worked example 14. A container in the shape of an inverted right cone. Okay, so that means that we've got a cone like something like this. Okay, with a radius of 2 centimeters. Okay, and a depth of 5 centimeters. Okay, is being filled with water. The depth of the water h centimeters. The depth of the water is h centimeters. The radius of the water is r centimeters. So we know that we've got some volume of water in here. That radius, that is r, okay, and this is h. Okay, we want to use similar triangles to express r in terms of h. Okay, so what we do is we say for our relationship, we say, well, r on h is the same as 2 on 5. Okay, so that we can say r is equal to 2h on 5. Okay, express, and then part B, okay, because part A was use similar triangles to express our r in terms of h, so we've done that. Part B is express the volume of water as a function of h. Okay, so remember that the volume of a cone equals 1/3 pi r squared times our h. Okay, so we want our volume in terms of h only. So this is where we're going to replace our r with this function here that we just found. So we can say, well, our volume now is 1/3 times pi times our 2h on 5 squared times h. Okay, so we neaten this up a little bit and say we've got v equals 1/3 pi times, well, we can say we've got 4h squared on 25 times h, which we can say then is going to be, we can say we've got 4 pi h cubed on 75. Okay, so we'll probably neaten up the best we can. Okay, and the last part of this question is, at what rate with respect to the depth of water is the volume of water changing when the depth is 1 centimetre? So what we want is we've got to find our rate of change of volume with respect to height. Okay, so we've got to find the derivative of this. Okay, so basically we've got to bring our 3 down. Okay, well, we can cancel that out with our 75 here to say we've got 4 pi h squared on 25 for our dVdh. Okay, and so we're going to find our rate of change when the height is 1. Okay, so we put in 1 for our height, so we get 4 pi on 25. Okay, which is equal to 0.16 pi. Okay, if we want to put in a decimal. Okay, so that means that we're changing at a rate of 0.16 pi centimetres cubed, because that's our volume, it's in centimetres, per centimetre in depth. Okay, so I know it seems a little bit weird, but that's the way we use it for our units. Okay, so we'll keep moving on. Okay, so we need to talk about kinematics, which is the study of motion. So it deals with displacement, okay, which is the distance something is from the starting point, not the distance something has travelled. Okay, so if we are here and we go wiggling around like that, Okay, well, our displacement is that distance, our straight line distance. Okay, if our displacement x is greater than 0, the particle is to the right of the origin. If x is less than 0, the particle is to the left of the origin. So we're just talking about something in our Cartesian plane here. Okay, our velocity, if velocity is greater than 0, the particle is moving to the right. If velocity is less than 0, the particle is moving to the left. Velocity is the rate of change or displacement with respect to time. Okay, so it's the rate of change of our displacement. Velocity is the gradient of a position time graph. Okay, so if we had a position time graph, okay, well, the gradient of that is our velocity. Okay, our average velocity will just be our x2 take our x1 over t2 take t1. Okay, our average speed will be our distance travelled over our time taken. Okay, so we'll keep moving on. Our acceleration measures the rate of change of velocity. Okay, and it's the gradient of a velocity time graph. So this time it would be velocity up here. Okay, and time down here. Okay, and the gradient would be acceleration. Okay, and just a little bit of information for you, because the area under it, okay, is our displacement as well. Okay, if our acceleration is greater than 0, the particle is speeding up. If it's less than 0, the particle is slowing down. Our average acceleration is going to be our change in velocity over our change in time. So just got one more worked example to have a look at. Okay, so we've got if a particle moves in a straight line such that its displacement x meters from a fixed origin at time t seconds is modelled by, so we've got a function x equals t squared minus 4t take 12, okay, for t is greater than or equal to 0. Okay, we need to identify its initial position. Okay, so our initial position is going to be when t equals 0. So when t equals 0, our initial position is going to be x equals minus 12. Okay, so which means 12 meters to the left of the origin. Okay, part B is obtain its velocity and hence state its initial velocity and describe its initial motion. Okay, so our velocity is our rate of change of displacement. Okay, so what we need is dx dt, okay, which is going to be 2t take 4. Okay, and we want to know where our initial velocity is. Okay, so we need to go let t equals 0. Okay, it means that our v equals minus 4 meters per second. So that's 4 meters per second to the left. Okay, and we want for part C is at what time and position is the particle momentarily at rest. So that means when is our velocity going to be equal to 0. So we need to set this equal to 0, our velocity. So say 0 equals 2t minus 4. So 4 equals 2t. So t equals 2. Okay, so after 2 seconds, okay, after 2 seconds, okay, it has momentarily stopped. Okay. Part D is show the particle is at the origin when t equals 6 and calculate the distances travelled to reach the origin. Okay, so what we need to do is we need to sub t equals 6 into our original function. So x of 6 equals 6 squared take 4 times 6 minus 12, which equals 36 take 24 take 12 equals 0. So that part is easy. Okay, so to start off with, Okay, the particle was at, because we want to find the distance, so not the displacement, the distance it's travelled. Okay, so we know initially it was 12 metres from the origin. Okay, it was going 4 metres per second. Okay, and it took 2 seconds to slow down. Okay, so we need to draw a little diagram, really. Okay, so at minus 12, okay, we started, and our origin's over here. Okay, so we started here, okay, and we went this way. Yeah, I just want to double check this. We haven't done our displacement after 2 seconds. Okay, so what we want to do is I'm just going to sub 2 back into our original equation. Okay, so x of 2, just so we know where we were, our displacement after 2 seconds, when we'd stopped. Okay, so when we do that, we get 2 squared minus 4 times 2, take 12, which is 4 minus 8 minus 12, which is minus 16. Okay, we haven't worked that bit out yet. So we're down here, we go down to minus 16. Okay, and we know at that point we stop, and that's when we turn around and we come back to the origin by our 6 seconds. Okay, so it has travelled all up, it's going to have travelled 20 metres. Because we're going to have gone 4 this way, then 16 that way. So our distance equals 20 metres. Okay, so then we want to calculate the average speed over the first 6 seconds. So our average speed equals our distance over time. We know our distance is 20 metres. We know it's been travelling for 6 seconds. Okay, so we know our average speed, when we do that, is 3 1/3 metres per second. Okay, and that's the end of that worked example. Okay, so look, hopefully that's enough to get you through this last section. A little bit of different stuff in here in terms of our rates of change. Okay, and there's always that great link of our displacement and our velocity and acceleration that we're always going to exploit for a lot of these questions. So expect to see on the exam or a SAC something to do with displacement, velocity and acceleration, because it will almost guarantee you that it will turn up at some stage.